So in this talk, we're talking about listening to consumers and customers. What information can we use in terms of data and in terms of survey responses to improve lives? So as an individual navigates the healthcare system, they have experiences ranging from hospital visits, pharmacy visits, clinical visits. They will call their insurance office for prior authorization for procedures. The types of data that we're working with in these cases are text from data, claims records from databases, and survey responses from individuals responding after a call. How would you rate your satisfaction with this company? How would you rate your satisfaction with this person you were just on the phone with? And in this talk, we're going to combine all of these different kinds of data to try and figure out how we can improve the customer journey so that they can, for example, be more likely to stay on their medicine regimen if it's not so difficult for them to be talking with their pharmacist, or if they have appropriate tools and reminders if they're all living hectic and very busy lives that they're about to due for a medical referral and they might need this service or this platform. The particular answer for how we're solving this is data. We have a lot of data at our fingertips. That's a little bit of a jest because data sitting alone on some server is not going to do anything by itself. It can just sit there and get stale really quickly. So we don't just need data. Advanced analytical methodology with that. So in this use case, we take survey responses that individuals put in for not just after a call or after an interaction with a system. They can also relate their entire relationship with a company or a platform. We take the open-ended answers, so what's your overall satisfaction with this website or any of that. We take open-ended text as well. We take chat transcripts and we run them through a natural language processing algorithm that outputs a sentiment score and categorizes a reason that the individual called that day. In addition to digital interaction data, so claims history, prior authorization, whether they used a website, how many clicks did they go through in the website, how long did it take them on different portions of the website, was their frustration detected and they quit and ultimately ended up abandoning the website. They weren't able to answer their question and then had to call on top of that, which, by the way, usually ends up in a very negative customer experience. But not only do you have to spend forever looking for something on a website, you also have to call in, spend forever talking to someone on the phone and still not get your question answered. We take all of these data together and do exploratory data analysis. So one, we just need to understand the data. It's a wide variety of data, wide variety of data types, wide variety of data sources. We need to go in and understand it. We run machine learning and AI on it, and we ultimately end up putting it into a large Bayesian network. And we use the outputs and the insights from the Bayesian network to guide NPS action planning. So individuals within the company who are responsible for putting in a new program, a new marketing platform, something to help people know that if we find a sticking point is they have medication renewals and they forget to renew their medication if they have a particular condition, possibly because that particular condition impacts their memory. So being able to detect things like that and figure out where the pain points are and use that to guide strategy planning. But in order to do that, there's a lot of slices and dices in looking at the data and trying to find those small sub-portions that are experiencing that particular thing can be very difficult, especially if you're taking all of the data and just putting it in as a vector. So Bayesian network analysis is an artificial intelligence tool for decision support under uncertainty. So environments where there's a lot of noise, environments where there's a lot going on and we don't exactly know what's happening because it's a very complex system. So imagine an individual who has to decide, you're the leader of a company and you decide what you're going to do to help improve the customer experience. How are you going to do that? One particular way is modeling the system. If you have a complex environment such as an ecosystem, you can take the complexity and boil it down to its essential elements. What are the key gears and knobs in this complex system? What are the main players, the main things that are happening? And put that into a model. So here's an example, a couple of examples of a model. A model is a simplified representation of some aspect of the world. You don't want it to be too simple and it's boring and it's not useful. You don't want it to be too complex because then you can veer off and essentially have something that isn't functional and isn't useful anymore. You can't model the world in its entirety. If I wanted to create a map of the world, I wouldn't want to know the elevation of every square foot of the continent of Africa if my purpose of the model is to travel across the ocean from the United States to Europe. I don't need the granularity of the model in that area. It's not going to add anything to it. In fact, it'll just add noise to the system. So here we have a chart and a graph talking about data and theory on the left. So it's an axis. Models can be informed primarily from data. They can be informed from human theory, human learning, human intelligence. Taking into account modeling purpose on the bottom, what is the goal of the model? What are you going to be using it for? Are what you're trying to do improve your accuracy on a coding problem? That's an association correlation problem. Most AI is in this left portion of this diagram. Supervised learning, unsupervised learning. Most machine learning is in that association correlation. Most of the field ignores this right portion of the diagram getting into causation, because causation in general, the gold standard for causation is doing experiments, and doing experiments in the real world is unethical, problematic. You can't put a group of people into a control and a placebo group or a control group with a treatment in almost any industry, in healthcare or in banking or in government. It's just not possible. So one thing that we can do is by combining data with theory, releasing the constraints of a lot of machine learning and AI, we can bring in causation by allowing the theory aspect to be present in the models. For a little bit more concrete of an example, the box on the left is a typical black box machine learning neural network approach. You have an input layer in a neural network, a bunch of features in your system. You have the neural net, the neurons in the middle that are doing incredibly complex math. And you have an output layer, for example, a classification engine. Is this image a dog, a cat, a coffee cup? The individual nodes in the middle are not interpretable themselves. And that's something that's different, actually, than Bayesian networks. The nodes in the diagram each have interpretable value in and of themselves. So the diagram on the right is a Bayesian network that characterizes someone's likelihood of having a couple of different conditions, tuberculosis, cancer, or bronchitis. They walk into your office, you might know a few things about them. You might be able to ask their age and get that information relatively quickly. You might be able to ask whether they're a smoker or not a smoker. You might be able to interview and ask their symptoms and see if they're coughing at that particular moment. Each of these nodes has a distribution in and of itself. The age of a person in this country in general, how likely are they to be between under 18, 18 to 25, 50 plus. The likelihood that they're a smoker, that's also a distribution. That's something that a human can have intelligence and know the distribution of, or something that you can learn from data. And the arcs and connections between these things are causally interpretable. Someone's age can influence whether they are a smoker. Someone, whether they smoke, can influence the probability that they have cancer or they have bronchitis. When you put it together in a network form like this, you can slice and dice the data in any potential way by clicking on these nodes and seeing the conditional probability of someone who is 18, who is a smoker, who is presenting right now, coughing in front of me in my office. What is the likelihood that they have cancer, bronchitis, or tuberculosis? What if there's a new piece of information and they tell me that they recently traveled to a country that has high risk for tuberculosis? Then I can update the probabilities of the rest of the whole network by adding that information in. Now, the example that we just went through was a network that was created by people. The distributions in the network, the arcs, those connections, causal inference between the different nodes in the diagram were created by people. We can also create a network by learning from data. We can use machine learning and AI to take those wide varieties of data sources that I mentioned in the beginning, call transcripts, claims records, a person's interaction with a website, a person's actual survey responses, and put it all together and have the machine learn the distributions of each of the nodes. Each individual node in this diagram started as a column of data and can learn the arcs in between it. So you combine information theory with complexity theory, and you have them pit against each other. You don't want a model that's so complex and fully connected because that doesn't tell you any information. A model that's fully connected is noisy and doesn't actually afford inference. But you don't want no connections at all either, because that also doesn't tell you anything. So you can use information and complexity theory to create a network so that you can go in and double click on each of these individual things. A person who went through and had this claims experience, who had this call transcript and had calls over 15 minutes, that individual is more likely to be a promoter and advocate for your company, more likely to be a detractor and prevent others from using your company, or to be neutral. You can use this to guide NPS action planning. So answer questions like, what is the cost of a detractor? What does it cost to serve a person who is having an unpleasant experience with your company and is likely to need follow-up conversations, follow-up questions, be able to navigate different parts of the website and need more one-on-one time and care? Detractors ultimately end up costing the company more than someone who is promoting and happy with your experience. So you can figure out, with all of the slices and dices of the experience of an individual, how can you guide them through the company and guide them through a journey in the most effective way? How can you take the feedback and use it to iteratively improve the entire system? We do that by creating a model and then using that model for these inference tasks. So you can machine learn the model and then use it by combining human knowledge. You can present that model in front of people, vet it, have them look at it and say, this makes sense, this connection doesn't make sense. You can use that then to improve the model and use it for inference. So questions like, what are the financial benefits of improving the customer experience? What processes or measures are leading indicators of future relationship NPS? You have NPS metrics for the past, and you know that the claims records and that calls lasting longer than 15 minutes in the past have indicated a negative customer experience. You can use that to forecast what your likely future NPS will be by looking at all of the conditional probabilities with all of the data put together. You can also look at what are the biggest risks with what you know and what you have at your fingertips between claims and call and all of these other things. What are the biggest risk factors for losing NPS? So you can focus on gaining, but also you want to protect points and not lose them as well. We have a few minutes for questions. Yeah.
For the Bayesian, do you have enough data to kind of prove out like the sequence of steps? Like it's almost like you're kind of saying, here's the sequence of steps that it takes, and then I'm going to predict X. But do you have that kind of data available?
In this case, yes. I'd actually say Bayesian methodologies traditionally require a lot less data to get to a network than a lot of other machine learning and AI methodologies, because you don't actually need data at all to make the network. You can make the network entirely on human expertise. That first model that I showed you was made entirely from human experts. So we surveyed doctors from across the field and said, of people that have come into your office in the past that have had this display of symptoms or were in this age category, what was their probability of having this condition or this condition or that condition? So you get each of those pieces separate. Yeah.
Thank you so much. You had talked about on the NPS slide, you talked about how you use exploratory analysis, machine learning, and Bayesian network. Doing this a bit of an ensemble of some sort to get a final NPS idea. I'm not sure if you're doing something that looked like all those tables are being taken into account to determine NPS score or something. Can you talk a little bit about how you go from taking information from each of these three sources of modeling, or you have your analysis and you have two types of models, and what are methods you're using to then arrive at
The question referenced, let me go back to here.
Exactly.
Yeah, we're using, well, one, you want to explore the data. So you always want to take a look at it, it's actually there, especially if you're not the one housing the data and the one responsible for the data, you might not be as close to it. The short piece to the answer to that question is a feedback loop where we incorporate very early on in the process and very frequently subject matter experts. So we'll run all of these analyses together, present results to the subject matter experts, get a feel for whether it resonates with them or whether something stands out as somewhat alarming or somewhat strange, and then they can come back and say, oh yeah, this makes sense, or this doesn't make sense, have you considered looking at this other data source and incorporating that into your model? And then you refine the model iteratively and bring that back to the final stakeholders.
Final type of question for me. So if the machine learning models and the Bayesian networks are not showing consensus, how do you reconcile them then?
Well, in this particular, the machine learning that we're running is part of the Bayesian network. So the Bayesian network can machine learn the structure, and then we can bounce that off of the subject matter experts. So they're all working in cohort together to provide insights and glean whatever the underlying truth is that the data is telling us. I always like to view it as an archaeologist trying to uncover a skeleton. We're not trying to create and manufacture the skeleton. The truth is ultimately under there. There's something happening in the world that are causing these things. We just want to uncover what the key players are in the system.